Slides. Have the slides for chapters 5 and 6 made it to the back?
Yes.
Are there extras?
Lots.
Great. All right. And this explains why there are a few seats left. Yeah, go ahead. That's 5. That's 6. And we'll do this here. All right. So I've written this sort of cryptic message on the right. We will be sort of using this as our crib sheet during today, and hopefully it will make more sense as you see examples of it worked. The quick summary of it is I'm putting these placeholders here saying there's going to be probability distribution of something given something and theta. And then depending on what the somethings are, we'll make a distribution on A using a function of B. So we'll take whatever goes here, that's what the distribution will be over, a normal distribution for example. And the thing that sits there, well that's what will be an argument to this function. So why we're doing that hopefully will become clearer now. We're going to have 3 types of models. The point of today is so that you understand the 3 types of models that we have. We will go through 2 examples of working with each of the models. So we'll do a regression example with type 1, with type 2, and then type 3. Then we'll do a classification example, again, with the 3 types. And then we'll discuss sort of how we choose them and why. All right. So you don't know what the 3 types are, so we're going to try to motivate that. From now on, throughout the whole term, we try to keep our notation as consistent as possible. There is one misprint in the slides that you're holding, where there's still a y left over from the old days. So when we get there, I'll remind you, so you can change it in your notes. It's already corrected in the slide. The notation we're trying to stick to is the observed data is x. It's either just a regular x if it's a single datum, in other words, a single number. And if it's a vector of numbers, we'll do it bold, or on the board, I'll do it with an arrow overhead to indicate that that's a vector. Okay. So we're going to observe data x, and we're going to try to infer things about the state of the world w for world. Similarly, either normal w or bold for world. All right, so examples are that you might see adjacent frames in a video, right? I give you a video, and you're trying to estimate how did the camera move between frame 1 and frame 2. So the inference part is this end part. That's where you deliver the solution back to me to the question, what was the camera motion? I might observe an image of a face, and I'm now trying to infer the identity of that face, right? And of course, there's lots of complexity behind this problem. How do I model the face? Am I trying to identify from a set of people that I know in this room, where the set is small, or out of the whole world population? Last example here, observe an image of 2 displaced cameras, and now I'm trying to infer the structure of the scene. Where are the points in 3D, for example? So we'll always have to kind of think about what is our x, what is our w, what are the dimensions of each, are they continuous or discrete? All right, so none of this should be coming as a shock now. We've done a little bit with fitting of probability distributions, but now we're actually going to start using it. Right, regression versus classification. There is, could I get people to slide down 1 in the second row there? So you have to see that there. The argument is both for your comfort, but also for safety in case there is a fire drill or something like that. We all have to escape. All right. So what's the classification and regression? Well, normally we might be dealing with a w that is continuous. In that case, we have regression. We're trying to come up with if W is not bold, so we're just coming up with a real number, for example, or if W is discrete, then it's classification. Now, this has lots of implications, so we'll spend a chapter on regression, a whole chapter on classification. Today, this week, we're kind of doing both because we're trying to introduce our types of models. Does this regression versus classification depend on what's happening with X? Whether X is continuous or discrete? Some nodding heads, one way or the other. Yes or no?
No, doesn't matter.
Doesn't matter. Right. It's about the world state. We're trying to infer the world state. The question at hand is what's going on in the world. So that's what determines whether we're dealing with a regression or a classification problem. All right, so the world is ambiguous. We might be getting X's that are noisy, messy, somehow even misleading. We might want to infer something about the world that is actually quite indirect, right? Companies try to do this all the time with targeted advertising, one of the biggest businesses now, right? How does your choice of searches on Google indicate the number of children in your household, right? So you might have all sorts of notions of things that are correlated, so you try to build them into your model, but your data might be ambiguous, and in the case of visual data, it's definitely ambiguous. You're losing frequently a lot of 3D information when you project down to 2D, and even if you have a 3D camera, well, then there's still lots of problems. You can't see behind objects. You get unusually high noise, things like that. So what we'll be doing is, instead of trying to come up with a single answer, well, sometimes you might have to come up with a single answer for what state is the world in. We'll try to keep a distribution on the world, right? This is why we introduced random variables in the first place, so that we have the freedom to say, for the world being in this state, I think there's a certain probability of that. For the world being in that state, I think there's a certain probability of that also. And we try to delay commitment as long as possible. If you can, you use the Bayesian model. If you can't, then you use something like maximum likelihood or maximum a posteriori. Right now, we're not going to worry about that. We're just going to keep in mind that we want to keep track of the probability distribution. What is the probability of the world given the data? Right. So we're going to refine our goal here. We're going to say we want to model the probability distribution of the world given the data over possible worlds that are compatible with the data. We might find that the types of data that we encounter are very limited, and that really limits the type of world we live in, right? Or vice versa. It might be that we choose that the world is only two kinds of worlds, right? There's capitalism and communism, and then you have a very simple, it doesn't matter what the data is saying, it's going to be a very clear-cut situation. If the world were so simple. All right, so in our solution, we're going to have a model. We've been introducing these already, right? So these are models for our probability distribution. We're going to have a learning algorithm. This is what we discussed for chapter 4, fitting of the parameters to a given model. And then we'll have an inference algorithm. The inference algorithm is what you do after you've seen all the training data, and then on the big day of the test, someone comes along and says, here's some test data, X star. Please tell me what is the state of the world. Not just the number, but give me the distribution of possible states of the world that we're in. So with these three ingredients, or these three components, we're going to launch in to describe the types of models that we have. So the three types, we're going to say that we're going to go in the same order. So if it's easier for you, just remember 1, 2, and 3. But the thing that sort of gives it away is this probability at the end. So the simplest one is going to be the probability of the world given X. Conveniently, it matches the thing we're trying to infer. We're trying to infer the probability of the world given X, and this first model does that directly without any sort of extra detours. The second model is the joint occurrence, so probability of X and W, right? So you should be seeing this quite clearly now this is W given X, right? So it's got a dependency. This is a joint dependency, and this is the probability of X given W. We're going to give these sort of higher level names, where the first one sits by itself, and the second two are joined together. The first one is a discriminative model, probability of W given X. We're trying to discriminate between the types of world that we may encounter. Maybe that's one way to remember it. And then these last two, joint probability and probability of X given W, these are generative models. So you could try to think of these as situations where probability model over the data. So we have a probability. Remember, this one is one where you might have a two-dimensional map with some sort of heat map, right? And we're saying, oh, I care about the whole map. I'd like to know all the information here, and I'd like to know for X and W what the probability is at every given location, right? The probability of X given W says, oh, I'm going to pick a certain W, I'm going to pick this scan line, and I'm only going to look at one at a time. All right. So we're going to go through these now in turn, but when we talk about discriminative, we're talking about this one specifically. When we're talking about generative, we're talking about one of these two. All right. This part about the generating new data, I think, will be quite cool when you see an example of it shortly. All right, so the first type, probability of W given X, the discriminative model. The steps are we choose an appropriate model for our probability of W. Just by itself, marginal distribution, probability of W. Then we make the parameters of that parametric function. Remember, we introduced those in the first week. We make the parameters of that function dependent on X. So they're going to take the X values somehow and help us compute where we are in this parametric equation that we chose in step one. And then finally, the function that is sitting in here, a function of X, it takes as parameters theta. Now this theta, I don't know if it's bold or not, but it will potentially have multiple parameters. So these will help us control this function, the function of X. When we're learning, the goal is to learn the parameters theta and make all of this fit together, right? I could make up a distribution here for the first step. Maybe I'll choose a Gaussian distribution. But if the probability of the world isn't Gaussian, or if it is Gaussian but I don't do a good job of associating where the bump is, where the mean of the Gaussian is with respect to the data X, this isn't going to be very useful a model, is it? So I need to make sure that I, at the learning stage, fit the parameters theta to bring the model in as close an alignment as possible to the data. Once I've done that, I throw away the data, right? I say, okay, I've got my parametric representation, that's all I've got to work with. And that parametric representation, as we said, is going directly for probability of W given X. So when someone asks, by the way, can you, at test time, at inference time, tell me what is the probability of W given X? We say, yes, of course, I've got it right here for you. It's not going to be so easy in the type 2 and type 3. So let's do type 2 briefly. We're going for the joint probability, X and W. Step 1 here, we concatenate X and W to make this new long vector of X's followed by W's. It's a pretty sleazy trick, right? Nothing fancy. We're just putting all the numbers together and saying, great, I have this new vector, we call it Z. We make a probability distribution for Z, one of the ones we've seen already. And just like before, we're going to try to fit the parameters theta so that the model that we chose does a good job of explaining Z. Then, once we've learned them, at test time, someone comes along and says, well, I didn't want the joint probability. I wanted the probability of W given X. Help me out. Well, you say, well, I've got the joint probability of W and X. Bayes' rule can help us out here, right? I have this term. I know that this term equals probability of W given X times probability of X. So I can just divide that term over here from Bayes' rule. So I divide probability of the joint probability by the probability of X, and I get probability of W given X, the thing I wanted in the first place. Now, this extra step, right? I'm computing. We're going to model this with our model on Z, but we have to remember to normalize by the probability of the data. We're saying, I've got this model. It tells me about all the different situations of X and W. Maybe I should maybe write it there. Right, but some of the combinations of X, they just never happen. That's just never occurs, right? So I need to take that into account when computing the conditional probability of the world given the data. And we all know that we can expand this bottom part, right? Probability of X is the same as the joint probability of X and W after we've integrated out what's happening in the world, right? So that integral over the world states leaves us with just probability of X. Yes?
Sorry, but I mean this assumes that the X vector and the W vector have the same units.
That they're somehow compatible.
Well, yeah, quite compatible.
That's right. Yep. So we won't always be able to make a generative model of this type where we concatenate, because maybe we have, yeah, that's right. So that's why we have a second generative model to handle those cases. Fair enough?
I mean, is that an advantage? I mean, if you have this situation, then you always go for this generative model as a rule.
We will come at the end to why we would choose one or the other, but the summary is no, there's not a good, strong rule. You can get into debates with people at conferences about whether this problem should be dealt with using a generative or a discriminative model and the pros and cons. The short answer that you've seen already is if you use the discriminative model, inference is easier, and potentially you don't need as much training data because you're just modeling the probability of the thing you care about at the end. Whereas in the generative models, you're modeling quite a bit more. You're modeling this joint probability, which means you have to be able to say something about how the data is generated. What are these probabilities of certain data? Whereas in the first model, the data is just handed to you. It's always given. There's no option to not think about how the data is given. It's just handed to you, and you don't question it. So we'll do a summary at the end describing sort of the pros and cons of the different models. But that's a good observation. All right. Type 3, and so we're just going to go 1, 2, 3, and then we're going to go through class example 1, 1, 2, 3, and we're going to go through example 2, type 1, type 2, type 3. All right. So I'm not trying to steamroll past this, but I'm trying to show them to you in short order so you can see, okay, there's sort of a progression, that they're slightly different from each other, and hopefully it will become clearer in sort of halfway through today. So our third type, which is our second type of generative, says, all right, what is the probability of X given W? Right. So we've got the conditional probability of X given W. We know we're going to eventually ask the question, what is the probability of W given X? But first, we've got to set up our model to represent X. We're saying, I'm going to think about the data here. I want to model a distribution that describes the data first. I'll make that model use a function inside of it, a function of W, because the W is what we're contingent on. And then, of course, we have parameters theta. We have to learn the parameters theta just like before. Once we've done that, now we can compute, if anybody asks, probability of X given W. Probability of the data given the world. So we can say, well, if we're in a world, if we're underwater, then the animal I see in this picture is a turtle, right? But if I'm above water, right, then the animal I see before me, I probably got this backward, is a tortoise. Is that right? Yeah. Got lucky. Good. Thank you. Right. So one lives underwater mostly, the other one doesn't. Okay. So I've got my probability of x given w. I come along and someone says, well, that's fine, but that's not enough. I want probability of w given x. And you say, Bayes' rule to the rescue again. I know that if I multiply this by the prior on w, times probability of w, right, that equals the probability of w given x times probability of x. And again, if I move that probability of x down to the denominator here, which is what this is, I can compute my posterior probability, the probability of w given x, the thing I was wanting in the first place. But I did so using a generative model where we were modeling the distribution of x's. All right. So those are our three types. Now we're going to go ahead and apply them. So I've already mentioned that this is the sort of direct way. The discriminative model is the direct way of getting our posterior probability of w given x. And the generative one is slightly more complex, requires Bayes' rule, but also requires sort of other care with your training data. So let's go through the regression example. I know classification seems simpler, but we'll start with the regression example. First, let's just remind ourselves of regression. We could say, right, we'll start with the univariate continuous measurement x. So actually that could be not bolded because it's univariate. And we're going to use this to predict the univariate continuous state w, so also not bolded. And again, we said it's regression because of what w is doing, not because of what x is doing. We'll get to this example a little bit later, but this is an example of regression. This is not univariate. So here we're trying to regress not one, but something like 21 different real values. The numbers we're trying to come up with are the joint angles for each of the major joints of the body, where our input data, our x, is this image, or this set of images actually in a video. So we have this fairly famous sequence. This is Hedwig Siedenblad, who actually might be visiting us in London later this term. So we have this sequence. This is just 2 frames from this sequence, and that's our x. Maybe we will pre-process the x. We'll talk about pre-processing sort of later in the term, but it's sort of no surprise, especially if you're taking image processing. You frequently take your data, somehow transform it into a vector of numbers. The most trivial way would be to just take the intensity values and stack them up in a very, very long vector. That's not necessarily the cleverest way of doing it. But let's say we have some black box way of converting our pixels into a vector x. In this case, they're doing some pre-processing and getting silhouettes. Our goal is to estimate the world state, where the world state is a vector of 21 real values, which are the joint angles of the major parts of the body. And here you're seeing this sort of funny stick figure rendered at the estimated joint angles, and you're supposed to say, gosh, it's not that far off from the input. It's not perfect, right? That arm is clearly not in the right place. So this is a fairly complex example of regression where you're trying to regress multiple values at the same time. This one also fairly complex. Here we're saying, all right, we're just trying to motivate you, right? Why do we care about these? Why do we want to model these distributions? So we're going to play this game where we're going to show you the frontal versions of these people. So this is a frontal version of one person. And we're going to try to predict what they look like at 45 degrees. In other words, we're going to try to generate an image of what this person would look like had they turned their head 45 degrees to the right. Now, for these particular individuals, we actually have the training data, right? So we have the observations x, and we have the output, right? The world is in this state, right? This is the world state, so this is x, this is w, for 2 individuals. We might make a distribution. This is a joint distribution, probability of x and there's a sneaky y. That is supposed to be, what is that supposed to be? W, thank you. So, Now, if it's still that way in the book, then that's going to have to go in the second edition. And there as well, right? Okay. So we'll have our joint probability for x and w. And then when we try to estimate what would a certain person look like, a new test person, right? We might go to this x and say, wait, I've got someone like this. I don't know what they actually look like. Can you tell me what they would look like at 45 degrees? And we would say, great, I'll just look at the distribution of what they might look like. This is the world state. And I might say, oh, well, the peak, that's probably the most probable appearance that they have at 45 degrees. Right? So there's a whole distribution. We're not saying with this that there's a single answer. Right? We could say that there's a maximum a posteriori answer. But we're saying, well, there's a whole distribution. So this becomes useful if you're trying to compare, right? I say, I've got this photo of this person at 45 degrees. Is this the same person? And you say, well, I don't know, but I can tell you the probability of that. And if they turn a little bit one way or the other, we can compute those probabilities. All right. So these are both fairly tricky examples. Yes?
So you're trying to generate that image below, or
Yeah.
you're trying to match it up?
Trying to generate.
Okay.
In this application, we're trying to generate.
Okay.
The reason it's interesting right now to us today is that we're talking about joint models which allow us to evaluate this. The mechanics of how to generate this, how to generate samples from this distribution, is a little more complex. We'll try to get to it. All right. For our purposes, maybe we care about the simpler example, univariate, so one variable in, one variable out. Okay, I lied. This is many variables in, one variable out. I just want to know the head angle. Is it facing forward? So that would be 0 degrees, or a little to the right, or a few degrees to the left. Okay? So you can think of how you might go about capturing training data for this. You go, capture some photos of people, tell them to rotate to look at some dots projected on the wall, right? And acquire a whole bunch of images of different people looking at different angles. All right, so maybe keep this kind of example in mind as we go forward. Let me just... All right. So we're going to make our measurement x to estimate our world state w, and we're going to do it 3 different ways. The first one is the discriminative way. All right, you've seen this slide before. We're going to try to choose a model that will be appropriate for our world w, right? We're doing probability of world given x. So we frequently choose the Gaussian, the normal distribution. You could say, if this is coming up quite a lot, the Gaussian is convenient, it's handy, it's numerically it's quite good, it's quite stable. But you should always sort of check your data before jumping in this situation, right? If you look at the world state and you see that most people are either looking way to the left or way to the right, then using a single Gaussian distribution to model that would be good or bad? Bad, right? Because you're saying, well, I think everyone's basically looking forward plus or minus a few degrees. So we're going with this assumption. It's a simple example. Please don't necessarily pull out the normal distribution every time somebody asks you to use a distribution, okay? All right. So we said we've got to pick a distribution. Now this is where this might be coming into play, right? So we get to choose which way we're going. Right now we're using the type 1 model, the discriminative model, where we've got probability of, that would be, should I use a different color? Probability of world given our data and some theta, right? And we're going to come up with a distribution on, that would be the world. In this case, we're saying distribution is this normal distribution, which is going to take sort of 2 sets of parameters. It's going to take a function on the data, and it's going to take theta, these parameters. All right. So we say, right, we've chosen our normal distribution. We're going to look at our distribution. It's a parametric equation. It's a normal, right? It's Gaussian. The mean mu, in our case, we're going to say, fine, it's a linear function of x. So can you see that in the back row? Yeah, it's a little thin here. So I'll read out phi 0, phi, right? Phi 0 plus phi 1 times x is the mean, and the variance is sigma squared. Phi 0 plus phi 1 times x. So we've got a linear function of x. I haven't told you what phi 0 and phi 1 is. You can bet that we're going to have to try to estimate those from the data. We're not going to dwell on that right now, but you've fit distributions to data before. You'll be able to do it again. The idea is that this is a Gaussian distribution on the first thing there. So it's a normal distribution on W, the world state. It has a mean and a variance because it's this parametric equation. But the function for the mean depends on our data x. Is this part okay? You understand why we have a function here? Yes?
I just don't see why you just decide that. It's not clear to me why you would just say like, well, the mean of the world is, given the data, is
dependent on this parametric equation.
Yeah.
Yeah, so we introduced our probability distributions so that we would have a basic set of parametric equations to model the probabilities in general. And now we're getting into the details. We're saying, well, I need some relationship to x.
Mm-hmm.
So if x goes up, what should happen to w? If your point is that that relationship could be quite a bit more complex,
Yeah.
then I would agree with you. It can be more complex. So if you wanted to have phi 0 plus phi 1 times x plus phi 2 times x squared, for example, you're absolutely entitled to do so. You're saying, you know what, I think it's not a linear relationship between x and the world. I think it's some polynomial relationship between x and the world. Absolutely right. We will get to examples of that in the regression chapter. So if you think you know something about the representation that better fits the data, you should absolutely use it. This is, in fact, maybe it should be emphasized better, this is the choice of this being a normal distribution, and the choice of the function that goes in here is very situation specific, and that's kind of why I'm not putting it here, right? This is the part that you should be doing. Let me erase this. And the choices, right, of whether you're doing discriminative or generative, and the choice of this function f are ones that will hopefully be clearer when you start looking at the data yourself. Okay? All right.
So could we in the same way complicate your value for variance as well?
We could. Definitely we could.
That would complicate things.
It would of course it would complicate things, but it may be your data is complex and you can explain it, so it's a good kind of complexity to explain. Definitely. Yes?
So can we map this to the head angle example? So the phi 0 would be, like in general, people like to look at a certain angle, like a general offset of
Yes.
that's just there, and
Well, everyone always looks to the right by 30 degrees.
okay, and then the phi 1 would somehow, okay, I have data, so I believe now it's a bit more offset, but somehow I have always this, so this constant variance means no matter which data I observe, I have the same uncertainty.
No matter which, this is a mean. This is going to, at the end of this, we're going to come out with a single number that is the mean, and we're going to then say, well, there's a certain variance around that. So our parametric model is just a normal distribution. It doesn't have very complex shapes, and so it is always going to be, I have some scalar mean, I have some angle that I think people look at, plus or minus some variance. Yeah. So we'll see this plotted in the next slide. What this looks like, but that you've got the right mapping between this and the head rotating example, right? We want to we want there to be a relationship so that when someone changes the inputs x, the world somehow changes. Either the world, the angle goes up or the angle goes down, and hopefully it does so more proportionally than not. The thing to point out now is we've got a few parameters to play with, right? So we've got phi 0, phi 1, and sigma squared, right? So phi 0 there, phi 1 there. This is a function that takes x. And we have our sigma squared that we determined was going to be useful for our model, our normal distribution. So typically, we just write all of these together as the theta vector. I use black, but so this is our theta vector equals all of those, right? It's going to be this set of parameters. So well, if you see theta as bold, that's probably saying, oh yeah, all the parameters of the model that you just established. Okay.
Sorry.
Yes.
But we don't really know what x and w is, so it's not the angle. It's just, well, w can be the angle, but x can be a lot of feature vectors.
It could be a lot of features, and in which case, if it's sort of more complex, then these might have to be vectors of parameters, not just a handful like they are right now. So this is why we're trying to do this with a simple example so that you can then see the plot, right? Because now it's low dimensional and I can plot it for you and you can see it. So what you should be seeing here is we're just plotting our conditional probability, right? This is our discriminative model, just repeating, right? Type 1, discriminative model, probability of w given x. We picked out of a hat, you could say, or because we had brilliant insight, we picked a normal distribution on w, where we said the w value, this is the y-axis, the w value depends in some linear fashion on x, because I'm going to choose these parameters so wisely. It's going to be this linear relationship with x, and the variance is going to be this fixed sigma squared, right? So when we look at it, and what we're looking at, by the way, is the blue are a bunch of training points, right? These are examples where someone handed us an x and the parent w and said, this is the data and this is the state the world is in. Yeah. Okay. So those are a bunch of samples. We looked at them because of our great wisdom and insight. We said, this is going to be modeled best with the normal distribution, and I'm going to, I think there's kind of a linear relationship between x. So x maybe goes from some small number to some big number, and it looks like when x gets bigger, the world gets smaller, right, in kind of a linear fashion. So we'll say there should be a linear relationship, phi 0 plus phi 1 times x. All we need to do now is pick a phi 0 and a phi 1 so that the line has the right slope and the right y-intercept. So you can think of phi 0 there as the intercept, the y-intercept on the y-axis, and phi 1 is the slope, the rise over the run, right? So vertical change over horizontal change. Now, we can fit the data. We can fit the parameters to this data, and we might then also say, I also have to fit a sigma squared because I'm going to use a single constant variance for all of the data, right? So you should be seeing now once this color version, right? Not the dots, because that's our training data. So someone hands us the training data. We say, I'm going to model this with a parametric equation, so I can throw the data away and just use these equations later on. So the colored version underneath is the parametric model after we've done the fitting. And if you look at this sort of stripe, right, you should be seeing that this is quite bright in the middle, right, and it gets sort of darker and darker towards the edges. And in fact, it should look like this kind of Gaussian at every slice of the way. The Gaussian has the same variance at every slice, so this will be the same shape all along. Nice thing is, now even if I throw away the data, I can keep it, I can throw it away, it doesn't matter. I can ask what is the probability of the world being in this state if I have an x like this. That would bring us here in this graph. We've never seen a data point there, yet we can compute some sort of posterior probability there. Right? Fantastic. This is the beauty of fitting a parametric model to our data, to our individual data points. Is this okay? All right, so we're just going to do this again. Sorry. Right. So the fitting of the parameters, we've seen a little bit of the fitting of the parameters. Right, so we can do a maximum and posteriori fitting of the parameters. Here, we're just showing an example where we're assuming that each of the data points is independent of each other. Not that they're independent of the process generating them, just that it doesn't matter what order we sampled them in, right? So they just kind of come to us willy-nilly. So here we have this product of probability of the world given x and the parameters theta times our prior on theta. And we're trying to maximize this probability by choosing the right set of parameters. So this might be how we figure out what phi 0, phi 1, and sigma squared is. Right. We're not going to worry right now about how the learning happens. We just will sort of agree that the learning can happen, at the end of which we have this graph, or the ability to compute our our model here, probability of W given X. It just so happens that once we've learned probability of W given X, when someone at inference time says, hey, what's the probability of W given X? We say, great, I can tell you. For a new data point X, I can look it up and I can just say, right, whatever here, look, right, I've got this distribution, this is what these are all the different values of W that you could have and their respective probabilities. Right? That one's quite probable, that one's less probable, equal to that, for example.
Using the face analogy, X is a particular face.
Yes.
And then you present it, and then you will read out W based on, you'll have an estimate of what the angle you think is.
That's right. So you will now say, I have, I think this is the angle of the face, but I'm not entirely certain, so I don't want to bet my life on it. I'll tell you what the spread is, what the variance is around that possible angle of minus 12 degrees. Okay. So, no surprise, we're going to go through the other two models. So the second one is the generative one, where we're doing things jointly. We're saying, what's the model on X and W jointly? We already said we're going to kind of cheat here. We're going to assume that these are compatible, because for our purposes, we are saying that X is univariate, single variable, and W is a single variable. We'll just concatenate them together, so we have a two-dimensional vector, convenient for plotting, and we're going to fit a model to Z, this artificial variable. If we fit a model like a Gaussian, for example, to Z, well, we're still going to have to estimate the parameters of that model, right? No surprise. So that will be our learning stage. At inference time, because we've computed this joint probability of X and W, but we actually at inference want probability of W given X. So this should always be very, very intuitive, right? Increasingly for you. You should know, at inference time, what do I want? Right, probability of W given X. Okay. At inference time, I'm asking what's the world state, right? I'm not asking what the data is. So at inference time, what's the probability of W given X? We already said, we're going to use Bayes' rule, right? We know the probability of W given X is just this joint probability that we computed normalized by probability of X. All right. So if we illustrate that on the same example, the same data points, so the blue dots are in the same places, we might use a Gaussian. So we now have a two-variable Gaussian, right? So multivariate Gaussian that's trying to explain our X and our W at the same time. We fit it to our data, and now we have this two-dimensional mu and this 2x2 sigma, right, that define the shape of this Gaussian. So that's essentially it. You can compare that. So this is what it looks like, sort of blown up. We've got this normal distribution on X and W, which is sort of a single vector mashed together. And I think I have a slide comparing that to what we had previously for the discriminative model, probability of W given X. Can anyone see the difference? Yes?
And in the right one, we assume, for example, for low X values, we can give estimates, even though we don't have any training data for low X values.
Well, we can always give estimates, but you're saying something more specific, aren't you? We can give estimates at low X here, too. But what are you saying about those estimates?
We give them a higher certainty.
Yes, that's it. So just to repeat that, I think it's a very important point, right? With our discriminative model, we were just saying, I just want to discriminate between low values, high values of W. I'm trying to explain that as well as possible. I don't want to get into the details of the joint probability. And so that was fine. It was okay. We fit a model. And now you can do regression, right? You can predict things at low x. You can still predict things at low x using the joint model, our generative model. That's no problem, right? We have Bayes' rule for that purpose. It's working. We can ask for low x's. But here it's saying, well, actually, that's very low probability because it has fit this Gaussian distribution right here, in part because we said, well, I'm going to assume very little. I'm just going to try to explain the data in this generative fashion. And here you could say, well, you handicap things because you said there was a fixed sigma. Yeah, that's true. So if you want a similar behavior, if you want to have a similar shape distribution, so the heat map is what I'm talking about now, right? The data is the same. If I want a heat map over here that looks like the heat map over here, I'm going to have to make the discriminative, using a discriminative model, I'm going to have to make it more complex. I'm going to have to make, more variables, more parameters that have to be learned at training time. And if you have to learn more parameters, right, then you need typically more data. So this makes things harder. We have 2 minutes. We're going to finish this example. Yes?
Just for short, because we could have used a double parameter model on the linear one too.
Right, we could use a double parameter, you mean more parameters?
Yes.
Yes.
We could have done almost the same with the. So if we have 2 sigmas and 2 means on the right side, would that be this?
2 sigmas. Okay, so now you're getting into a more complex model where you have like a mixture of Gaussians. This is what we will be doing on Thursday. Yes, this is very good. Okay, so the type 3, the other generative model, right? So remember, we're saying this is probability of x given w, the probability of the data given the world. Remember this, right? Just fill in the blanks, but fill them in differently. Right? Probability of x given the world, so we need a probability distribution on x, right? We say, okay, maybe I'll pick Gaussian just for convenience. I'll make, because I'm doing regression, I'll make this function a linear function of the world. So we're saying, let's just get to the point. We're saying, all right, my distribution on x. Okay, my distribution on x is this normal distribution. It takes as it wants to know what's the mean, and you're saying, there's a linear relationship between the mean of this distribution and w. It's controlled by phi 0 and phi 1. And we're going to have a constant sigma squared. This should look very familiar, but remember we've switched places now. So these parameters, phi 0 and phi 1, will not be the same as if we had done it using the type 1 model. But we happen to have the same number of parameters. Right? And when we plot this then, we have our distribution, probability of x given w, is our normal distribution. Except now when we say, all right, for a given x, what is the distribution across the world state, right? We will have a very similar shape, but it's oriented this way. So our constant normal, or Gaussians of constant variance, are all oriented this way, which doesn't look that different actually, if you compare it to your original discriminative model. But remember, we still have to do this more complicated thing because at inference time, because we're going from probability of x given w to try to get probability of w given x. So if you want to see the relationship between the 2 generative models, that is illustrated, I think, beautifully here. Remember, this is our generative model we just introduced, probability of x given w. You have to apply a prior for it before you can compare it to the joint probability. So the joint probability of x and w really is, by Bayes' rule, probability of x given w times probability of w. Here we're introducing some prior on w, like a Gaussian. You can use something else. And if you take that, multiply it by your prior, this is what it will look like. So we've seen this one before. We modeled it directly last time. We can do it separately, though, as this term, sometimes called the likelihood, probability of x given w, times its prior. All right. So at inference time, like I said, we take the thing we just computed times its prior, normalized by probability of x. Good? That's the regression example. On Thursday, we'll continue with the classification example. Thank you very much.